Hi, I'm Chris Rackauckas, and I'm going to be your instructor for 18337/6338, which is Parallel Computing and Scientific Machine Learning. If that's not the class that you're looking for, then you're in the wrong classroom. So what I'm going to be doing today is I'm going to be discussing how this course is going to be run, right? Because this is the fall 2020 version of this course, and so it's going to be different than all other times. So the way that we're going to be doing this course is going to be through a lot of these videos, right? So we're going to have a lot of these videos and then a lot of asynchronous chats, and then we're going to have a lot of office hours to be able to get one-on-one discussions, or even just a few students at a time discussing. I think that this would just be a better way to be able to get very high quality versions of the material out, right, with videos and high quality lecture notes, and then we can use the actual time that we have together to really discuss the materials at a higher level, or at a deeper level. Actually, we can use all the time we want, right? So we can go really deep into the problem, we can be pair coding, and we can do all this stuff that would actually be pretty hard to do in a standard lecture setting. So what I would like to do for this course is take you through two disciplines in their own right: parallel computing and scientific machine learning. So parallel computing is the science of using multiple computers or multiple cores or accelerator cards in order to accelerate a computation. Now, it's not just engineering though, right? So it's not like we're just learning how to use a software to make this compute. This parallel computing actually requires that you understand your algorithm at a deep level to be able to change how you're doing the computation in a way that is amenable to parallel computing. So you're going to have to understand algorithms in a way that is about data flows and how we can split data flows and what things can be computed in parallel and which things cannot. And when there is a non-parallelizable algorithm, how can you rethink how you're doing the computation such that you do get something parallelizable, and what are the trade-offs when you do this? Right, so there's a lot of thinking that you have to do about how do you make parallel computation happen in a way that is efficient, and you might need to really change the algorithms that you're looking at, or look at completely new numerical techniques in order to do parallel computing effectively. Now, if you're going to do parallel computing, you have to have something that you want to compute, right? And for that subject, we're going to be looking at scientific machine learning. Now, scientific machine learning is different from just your traditional deep learning, right? So deep learning has really revolutionized how people look at things like natural language processing or image processing, right? So those fields have been completely revolutionized by how people can now take a convolutional neural network and just slap it in there and train a big data set, and boom, now it works, right? That's not the machine learning we're going to be looking at. So scientific machine learning is more focused on scientific computing mixed with machine learning, where scientific computing is the discipline where you look at things like dynamical systems, climate models, quantum mechanical simulations, partial differential equations, these kinds of equation solving and simulation that normally shows up in computational physics, computational chemistry, and engineering fields, right? So traditionally, these have always been kind of different, right? So you in a sense, in your engineering classes and in your computational physics classes, you are using differential equation solvers, you're looking at partial differential equations, and then you go over to a machine learning course and you're doing LSTMs and you're looking at convolutional neural networks, right? Well, what the field of scientific machine learning is doing is it's bringing these two together, right? It's saying that these are not, there are aspects of machine learning that can really be helpful in the way that we do scientific computing. So you can do things like utilize neural networks inside of differential equations to be able to learn missing equations, automatically learn missing physics. You can use it to accelerate some physical simulations, and you can use it to do all sorts of different things. So this is really what we're going to be looking at, because it's a very, it's a hot topic right now, which is part of the research that I'm currently doing, and it requires a lot of careful computation. You have to make sure that you build an entire source that is differentiable, which is something that I'll define later. So you have to have a whole differentiable code base. You have to make sure that you can train neural networks within something that is an inherently serial computation, like an ordinary differential equation. So how do you mix GPUs and serial computations together? And how do you then split this across multiple computers? And how do you make this so that way this very seemingly intractable problem becomes something that you can just solve with 30 lines of code with a library that you build, right? And that's really the key of what we're going to be doing in this course. So in a lot of places, you might learn how to just use PyTorch or just how to use TensorFlow. And you'll be told that, something special, this backpropagation goes on in the background, and you do a few theoretical computations, and now you're supposed to just use the library. But this is MIT, right? So we're the people who build things. And I mean, I myself has built a lot of these libraries. So what I really want to impart onto you is the knowledge of what's going on behind the scenes, and let's build this on our own, right? So a lot of these problem sets in the homeworks are going to be going towards building the building blocks, like the foundations of what goes on behind the neural differential equations. So how do you define a neural network inside of differential equations and train the two in tandem? How do you do this almost from scratch, right? And we're going to go through everything about forward automatic differentiation, adjoints, how adjoints are related to reverse mode, through how do ordinary differential equation solvers work, what are adaptive algorithms, how do you do error estimates. Then we start putting this together, and we start putting our ordinary differential equation solvers on GPUs and start stacking all the way up, so that way we have something that can automatically learn physical equations from time series data. So that's really what we're going to do here. There's going to be some of this in the course that's going to be geared towards how do you actually do this in practice, because we'll be building tools that are going to be useful for your own practice. But a lot of this will be going towards here's how things are actually working, because you might want to be a researcher who goes deep into this field. And if you want to solve the deep problems, you can't just use the surface level, and you can't just pick up the easiest tool around, because those things have already been done, right? I want to bring you to the novel part of the field. And so a lot of what we'll be looking at is how can you do a lot of fairly efficient coding so you can build something that is useful, but also connect that back to the mathematics, so that way you're solving new problems with efficient code. And then, when you put those two together, that's how high quality scientific software is developed. So, this whole course is going to be mixing these two topics of parallel computing and scientific machine learning in a way where it's all going to be about how do you do high quality, high performance software development for scientific computing or scientific programs, because that really is the driver of a lot of modern research. So the way I'm going to be able to do this is I'll be doing a lot of live coding sessions as part of these talks, right? So these videos will be a lot of showing a lot of the techniques and discussing lecture notes, but I really want to make this about live coding. I really want to show you, in real time, how do you do things like how do you profile your code, how do you write functions that are running in parallel, how do you understand that this parallel function is actually implemented in a way that it's actually going to be efficient enough, right? Because you can do parallel computing in a way that is just bad. You can do parallel computing in a way that is slower than someone doing just good serial computing. So what we really need to do is we need to make sure that we're doing everything in an efficient way. And there are really 2 or 3 programming languages that people usually look at in this field to be able to get something that is a very efficient parallel code. You can use really Fortran, C++, or Julia. Now, there are some fans of Fortran around, and I used to use a lot of Fortran, but I'd say it's probably not the best teaching language these days. And C++ is fairly... C++ just has way too much in it. If you like C++, then that's good for you, but it's not the easiest language to teach. And I think that if you know C++, you know exactly why I would say that. So now Julia is one of these newer programming languages, and it has a lot of the parallel computing built in. It makes it easy, so that way you just say add MPI, and now boom, you have MPI working on your local machine. It has all this kind of stuff to get you working in a environment that feels like R or Python, except you're doing high performance parallel computing. And so we're going to be using Julia as our platform here, and we're going to be using it in such a way that it's not just a surface level. We're not going to just glance over the fact and say, oh yeah, Julia's a little fast. No, we're going to go into this, right? The purpose of this course is really to have you learn how the mathematics is going to be moving to efficient computation. And so we're going to be within the first week here looking at how how a compiler is actually outputting this assembly code, and what are things inside of this assembly that are making it compute faster and slower, and how do you affect the assembly code that's being generated, right? And this is why we're working at a level where we can actually look directly at the assembly code and understand things about SIMD vectorization, right? Things that are fairly hard if there's no compiler involved, or if the compiler is baked into some accelerator and not truly a full part of the language. So if you're not familiar with Julia, the next video that will be coming up will be about how do you install Julia, how do you get it working, and the first lecture that we'll be going through will then really take you through a deep dive of the language with high performance coding in mind, right? Really, what I want to teach you for this language is, you should learn multiple languages in your life. And so if you already know Julia, that's great. If you don't already know Julia, well, it's a good time to learn a new language. And more so, I think that the interesting thing here will be to learn how a language with an interactive compiler is generating code and what that says about the performance of the code. So what I really want to take you through is an understanding of what does it take to make a scientific machine learning library not just work, but work well. And so what we're going to be doing for this course is we're going to have all these videos, and then we're going to have a live Slack environment. So on the Slack environment, I encourage you to watch the videos at your own time, because I know that different students will be in different time zones. And the Slack will be there for asynchronous communication, so we'll have a bunch of different channels for different lectures, and for problem sets, and just for discussing different topics. And I'll be watching this all the time, and as you ask questions, I'll be able to just chime in whenever I'm available. If you ever need me, you can just ping me, right? And then we'll have drop-in office hours. The times at which those will occur, we'll need to get a poll together to find out when will be best for everyone, since we have a pretty large class. But we'll pick a time that works for as many people, maybe 2 time slots. And if you're available, just jump in on that time slot, and we can do more Zoom calls or more one-on-ones and things like that, to be able to still have that actual discussion experience with in a synchronous way. But a lot of this will be going through a lot of these pre-recorded videos and asynchronous Slack computations, so that way you can work it into your schedule at any time, given this crazy environment. Half of the assessment will be based off of homework assignments, but what I really want to do with this course is I want to make it very research focused, right? Because most of the students here are graduate students, which means you're trying to focus on your research. And I can see that a lot of you are in computer science or engineering disciplines, where scientific machine learning and parallel computing can actually be used in your projects, or in your actual projects. So half of this course is actually going to be geared towards a final project, which is going to be about writing some paper on using some method of scientific machine learning and demonstrating it as some efficient implementation, or some new implementation of a new idea, right? Given what we saw last year from this course, a lot of you can probably just take your results from this final project and directly put it to archive, and then put it to a conference. So that's kind of the level that we'll be looking at for this final project. And it's not it's not going to, you're not going to just be on your own. You're going to be very guided to get to that level. So if you're an undergraduate and you've never written a full paper, don't be scared. What we'll be doing throughout this course is guiding you through the ideas of how do you do research, and how do you then try to find an interesting problem, and how do you then solve that problem with new techniques in a new efficient way, and demonstrate that your results really change some discipline. So as the syllabus says here, the lectures will all be pre-recorded online. So if you had some kinds of schedule conflicts, you can not worry about that. You can schedule something over our chosen time for this course, because that chosen time will not necessarily be used, though maybe that might become our office hour time. We'll have to see from the poll. So the office hour times are TBD. And the prerequisites for this course is we don't really expect everyone or anyone really to have the full range of topics, right? So high performance computing, numerical analysis, and machine learning are all going to be involved. And if you have background in one of them, you're probably good, right? So you should probably have a background for one of them because this is a graduate level subject. So you should already know how to do high performance computing and use that as a jumping point to learn the other two. Or you should be very good in machine learning and then, be picking up numerical analysis, or, it's good to have at least one base. But don't feel bad if you don't know machine learning already, or if you don't know numerical analysis already. It's expected that most people will not know this range of topics, and this is what this course is for. So there's no real textbook for the field of scientific machine learning. Helpful resources I would point to are Hare's books on solving ordinary differential equations 1 and 2. Those are the tomes of differential equations. So if you want to sit down and read something during all this lockdowns, those are the books that I would say, like, they're great. Gilbert Strang, also has the computational science and engineering. It's much more broad in its view, but it still has a very nice focus on the things that are required for doing high performance computing in scientific computing. The articles on machine learning are not really as relevant to the way that we'll be using it here, and you'll find out why when we start getting into the first courses on how we're using neural networks in somewhat of a different way from a lot of traditional machine learning. The grading will be, as I said, it's mostly based off of this project, and so it's 50% on the problem sets, 10% on a final project proposal, which is really just a one page just describing what you will want to do for your final project, mostly just to make sure that you're picking a project which is doable and you're starting to make some progress on it, and then 40% will be on your final project. And a little bit of details on that will come soon. And the collaboration policy is just that you can work together on your problem sets, but you should be writing it up on your own. Now for the final project, it's going to be about a 10 to 20 page paper in the style of some journal. So I say SIAM Journal of Numerical Analysis, but you can choose, NeurIPS format. You can choose whatever journal format you're kind of used to or interested in, or hopefully you're actually using this to go towards a real journal publication anyways, and so you just pick a format that is towards the journal that you want. The key to this is really about a high performance implementation of some algorithm in a form that is usable by others, right? So what I don't want out of this is I don't want a purely theory like, oh, this could be a good way to do computation. A lot of people say that a lot of things are a way to compute something, and they aren't right about it. What I want you to do is I really want you to say, like, this is a good way of computing this. I created an efficient implementation using these ideas. My performance analysis shows that this is probably the fastest I could implement it. We'll be going over how do you kind of prove these kinds of ideas, and then showcase some real result you can do with this, right? So either just show, if it's new sorting algorithms, new parallel sorting algorithms, just show that you can do something really fast, sort something really fast. You can also just take a look at some application, and you can do something like, take a biological model and investigate which algorithms would do best on it, and show how you can get a very fast parallel algorithm for doing parameter searches on this method, right? Don't feel bad if it's something that comes from your research. That would be something that I actually would enjoy to see, right? So don't go out of your way to make this not with your research. I'd say instead of go the other route, make this related to your research. So if you're already doing research in some biological network, or if you're already doing research in climate science, bring that expertise in, look at a problem that you actually care about, and spend the time to take a look at that and say, what is a portion of this that where I can really increase the very much make better the way I'm doing this computing, and take that portion and make that be your final project, so that way in your actual research you then have this product to be able to keep your research, make all of your future research faster. So I want it to be useful to you. Don't feel like you're double dipping in a bad way. If this ends up being useful to your research, this is exactly the thing that I want. So some examples that I've seen before are things like high-performance PDE solvers for specific PDEs, like Navier-Stokes, right? So it doesn't have to be a novel research project, right? This is more so to understand that and to really get a chance to really utilize everything that we talk about in this course. So you can pick something like, here's a really nice paper on a high performance method for solving this PDE. What I'm going to do is I'm going to implement it. I'm going to make a parallel version of it. I'm going to make sure that it's as efficient as possible. I'm going to turn this into a package. I'm going to benchmark it, and then I'm going to release this for everyone to use. I'm going to write it up and say, here's my new package for solving this PDE in an efficient parallel way, right? So that would be a very nice project where it doesn't need to be a brand new method, but it is still, it's a usable high performance code that really captures a lot of these ideas together. So other common high performance algorithms are a great one to look at, like Jacobian free Newton Krylov. Those are used in a lot of climate models. So if you're interested in how do you do very large PD solving, take one of these projects in that area. Recreations of parameter studies are really nice ones because, right now there's a lot of reproducibility crises, and one of the reasons why is because parameter studies are one of the most difficult computational things to do, because sometimes you need to search a 200,000 parameter space to be able to figure out where is the global optimum in this space. And so in biology, pharmacology, some aspects of climate science, there's a lot of these parameter studies which are not very thorough, right? And if you're in these disciplines, you can probably point to one paper already. Take that paper, implement their model, parallelize a very fast parameter study, throw neural networks to accelerate it in there, all sorts of things, and just see what you get. See if you get a result similar to theirs, see if you get a different result. That'd be a fun study, and it's a good way to be able to end up with usable tooling at the end. You can also just take a look at some of these methods that have come out that utilize differential equations and machine learning together. So augmented neural ordinary differential equations are one of these methods where you have neural networks inside of differential equations, and you add a few more differential equations to it to be able to get a universal approximator defined by an ODE solution. If that made no sense to you, that's okay. If that did make sense to you, you could do a quick implementation and then see, do a bunch of benchmarking. Is this idea actually useful for image processing? Is it actually useful for automated equation discovery? Yes or no. Look into all these different details, and that could be a nice project. So I'm not going to go through all these ideas. There's many in here, but you can see that it's really all about you take a problem that you think is useful, either one that is just like a methodological problem or one that is just about an application, and you come up with a code, you do a good implementation of it, and you write up what you did. A lot of these can probably just be directly released as packages, and you could probably get a paper right away off of that package. If that's what happens, that is perfect. That's what we're looking to do out of this course. We want high performance usable code to be what comes out of this course. So you can do it towards an application, or you can just try to do a state-of-the-art performance engineering problem. So we're going to be discussing about some issues like how do you do efficient cache usage inside of a linear algebra, right? So how do you do things like SIMD? How do you make your code SIMD very well? And so there's a lot of problems where there's some people have really poked at the assembly and made some really fast stuff for BLAS, right? Which is these basic linear algebra libraries. And if you want to take a shot at it, try to make your own type generic BLAS, or try to make really fast FFT algorithms, right? So these very basic algorithms, you'll learn how they're basic algorithms, right? Like mathematically, you can write down a very simple description of what's going on, but the actual implementations for how this is done in practice is very optimized to the extreme. And so if you want to take one of these problems, like how do you do a map reduce in parallel very fast and just create an implementation that's really good and write up all the details about what you did, those would be great final projects. And lastly, scientific machine learning itself is a very new field, and there's a lot of low-hanging fruit. You can probably just sit down for a week and then figure out like, hey, here's some new training techniques on physics-informed neural networks. And you can make your project just be. I tried 4 new techniques that came to my mind. It seemed like they did worse than everything out there, right? And that's still an interesting thing to write up and have as a final project, right? What are new methods to accelerate adjoints of ordinary differential equations? What are new applications of a neural differential equation? What are ways to be able to do parallelized implicit ODE solving on large ODEs? Like all these different things where some of these have been around for a while, but there's still a lot of low-hanging fruit. If you just change ODE to delay differential equation, suddenly there's not really that much that's been done out there in a large-scale parallelization of it. So you can pick one of these topics where it just kind of has a lot of low-hanging fruit and just say, I'm going to create a really nice code, and I'm going to see if this works out better than the naive thing. And if it does, hey, that might be a nice little project. So you'll have to come up early with what your final project abstract will be. It's really just one page to say, what thing in this giant world of possible problems do you want to work on, just to make sure everyone has a clear focus on what we'll be doing for the second half of the course. So the schedule of topics is that we're going to be walking through scientific machine learning and parallel computing in a way that is kind of in lockstep, right? So first I want to really introduce what is scientific machine learning, right? I've kind of given it a high level, but I want to really go through some of the recent results in the field to really give an understanding for what are some of the things that you can do with this discipline, right? That's probably why you'll care about it. What can you do with a physics-informed neural network? Why should you care about a universal differential equation? And with that, then we're going to start going into, we're going to build from the bottom up. So the first thing that we're going to understand is, how do you write really good serial code? So one thing that we're going to be doing here is that all the codes that we're going to be developing are going to be compatible with actually being a package that can be released. So I want to walk you first through, how do you write code in a style that is going to give you, usable packages that other people can then directly download and utilize. So once we have that, the thing that you're going to need for anyone to actually care to use your code is it needs to be fast. So how do you optimize serial code? That is actually a fairly deep topic. And then there's the first thing that will come up is, well, a lot of the serial codes that are out there that are used in scientific simulation are discrete and continuous dynamical systems. Ordinary differential equations, stochastic differential equations, all these kinds of objects are very serial in nature because they have this time stepping. You calculate one thing, and then you calculate the next, and you calculate the next, right? So these are very good examples to figure out how you make sure that you get a very efficient code for doing something that goes through time that requires what happened in the last time step, right? Because it's going to be serial, but you're going to need it fast. How do you put those two together? Then we can start to work in some parallelism, right? So what are the different forms of parallelism? What applications can do well with different forms of parallelism? And the first thing that we're going to start using in terms of forms of parallelism will be multi-threading, right? So almost all of you are going to have a computer that has multiple cores on it, right? Maybe you just have a hamster wheel somewhere that's... No, your computer has multiple cores, right? This has been this way since 2006 or something like that, right? Everything is multi-core now. So why do you not always use parallelism, right? Like literally every computer that you use it has parallel computing already ready for it. So what we're going to be first looking at is, how do you do multi-threading, right? How do we make it such that every single computation we're doing is multi-threading? And what are the things that we need to think about when we're multi-threading a calculation, right? How do you do it? How do you make it efficient? How do you know when it's even possible? And how can you change algorithms around such that they're more multi-threadable or less multi-threadable? Also, then at the same time, the story of linear algebra will have to be talked about in there because of how linear algebra libraries and matrix multiplication and multi-threading, they really work in together. You might have not even known it, but when you're doing matrix multiplication in pretty much any language, R, Python, MATLAB, any of them, your computations are by default going to be multi-threaded. And when we go through how you do multi-threading, it should be, and a lot of these numerical linear algebra algorithms, it'll be very clear why all of them are multi-threaded. And so the next thing that we're going to be looking at is we're going to start going deeper into the methods for continuous dynamics. So we're going to look at ordinary differential equations. So how are ordinary differential equations used? What are a lot of applications of them? How do you start to solve them, right? So there's if you're to open up MATLAB, right, there's ODE 4.5. And you might have been taught Rackauckas to fourth order. Maybe you haven't. But a lot of people don't seem to know exactly how ODE 4.5 works, right? How does dupree inside of Python's scipy work? Well, we can dig into those algorithms, right? So it's a fifth order algorithm which uses an embedded fourth order algorithm to get an error estimate, and it uses that error estimate to adapt its steps. And so we really want to go through how exactly do these very core algorithms for scientific simulation, how do they work? And now that we have this lens of parallelism, in what ways are they parallel, in which ways are they not parallel, and could they be changed to be more parallel? And then we want to start going into stiffness, right? So, if you know ODE 4.5, then you probably also know ODE 1.5s, or you've heard of LSODA, LSODE, CVODE, these methods for stiff equations. How do they actually work? You might know a little bit about how, the theory behind implicit Euler, and maybe have implemented a simple version where you have backslash in there or something. But the way that you create a very efficient stiff ODE solver is very intricate. We won't be able to go into all that in a semester course, but what we will do is we will go through a lot of the basics about what are the ways that you have to think about optimizing this kind of code, and then what are the mathematical techniques that start to work their way in. And so we'll see that forward mode automatic differentiation will just kind of come up as one of the things that you start to do inside of these computations. And these things like sparse differentiation, how do you, graph coloring problems start showing up, these NP-hard graph coloring problems start showing up as sub-problems in terms of how do you get sparse Jacobians faster to be able to solve a stiff ordinary differential equation in an efficient way. So this becomes just like a jackpot of huge amounts of problems, and we'll take bits and pieces of them to really understand what are some of the pieces that are used, to mathematically come up with a computationally efficient algorithm. And then how are they used, how are they optimized by thinking about the aspects of parallelism and then the compiler technologies that are built alongside it to be able to do higher order optimizations. And so this is going to start getting us to a point, though, where we can start to mix in estimation and our dynamical systems, right? So we can have, a biological model, and we can have data, and we can start to learn what the parameters in the biological model are from the data. And this starts leading us down the path of differentiable programming. So with differential programming, we're going to start looking at what are the adjoints of methods, right? So what is the adjoint of a nonlinear solve? What is the adjoint of an ordinary differential equation solve? And we're going to see is that reverse mode automatic differentiation is this idea that where adjoints and backpropagation, right? So neural network backpropagation are then the same idea. And this is really where we start to connect these disciplines, right? So we have parameter estimation and adjoints in ordinary differential equations, and you have training for weights and reverse mode AD or backpropagation on neural networks. These really come together to be really the same idea. And this means that you can start to put neural networks inside of differential equations. So neural ordinary differential equations then really come out of this idea. And this is something that you can use as like a continuous recurrent neural network, or you can use it as something that can be used to predict time series or learn physical laws. There's so many different things you can do with this object that we'll be exploring. Then we'll start to, now that we have neural networks involved, something that will come into play is array-based parallelism, right? So there's a lot of parallel algorithms that work if you have very large arrays. Matrix multiplications are very parallel, but also a lot of things like broadcast operations, LU factorizations. These are classic, very parallelizable algorithms. And so there's a lot of very nice things that you can do with getting free parallelism by utilizing the array format. This is one of the things we'll be looking into. And then we'll be starting to get towards distributed parallel problems. So problems where you want to use multiple machines. For people who want to do distributed programming as part of your final project, we can get you a setup on the supercloud for this. So we can get you onto the cluster, so that way you're writing MPI on 30 computers. If you aren't really going to be using that for your for your final project, we do have it so that way a single line of code will then install all these utilities on your local computer, so you can at least learn it all and test it all out locally. So you don't have to get onto the HPC, on the high performance computing cluster, if you don't want to, but through this course you'll have access to it if you need to. So let me know if you want access, and we can start getting your application in. And so what we'll be doing is we'll learn how to do MPI, right? So MPI is this thing where you have multiple computers or multiple processes run the same piece of code all at the same time, giving each other signals and telling them when to wait. And so you can, this is how climate models are programmed to use thousands of cores. And really what I want everyone to do leaving this course is you should know how to parallelize, one computer well and thousands of computers well. And so this distributed parallels of MPI is really going to be the key there. And we'll be looking at some of the classic examples of very highly parallel algorithms that people use in these MPI scenarios. Once we start to have that, we'll have our grab bag of different methods that people use for parallelism, and then we can start going through scientific machine learning with an eye for how to, spot algorithms that should be parallelized and start to make them more efficient. So we can go through physics-informed neural networks, how you do automated discovery of equations, how you can regularize equations with partial differential equations, how discretizations of PDEs are related to convolutional neural networks, all these kinds of higher order ideas, and how do we mix in GPUs into the algorithms that we're writing, and how do we then mix in parallel mini batching on multiple computers. It's really just going to be doing MPI plus GPUs over neural network training. And once you start layering all this together, then you start to get things that are very usable and production ready already codes. Then we're going to start to look at ideas that are very close to parameter estimation that are really starting to be used a lot more in these topics of scientific machine learning. So probabilistic programming, which is Bayesian estimation on programs. How do you do estimation of parameters within any code in a way that is probabilistic? And we'll notice actually some very interesting things, like the way that these Markov chain Monte Carlo methods are working. They're actually using ODE solvers on the hood. So we'll get to an example where we have an ODE that is defined by neural networks that is trained by a probabilistic algorithm that it actually ends up being an ODE solver itself. So differential equations really do show up in a whole lot of places, and this, as we start to get to the end here, you'll see that there's a whole lot of layers in that. Local optimization itself is a differential equation solving where stochastic gradient descent is Euler's method on the ordinary differential equation defined by the gradient to the loss. So we'll actually demonstrate some of these properties a bit more. And lastly, what I want to end with is how do we globalize our understanding of models, right? Because a lot of neural network stuff and a lot of current machine learning is very local focused. There's a lot of focus on, for the given parameters that I chose, do things work out? But what a lot of people are interested in, especially in things like pharmacology, are, for this model, is it safe? Is this choice of interaction with the system safe? And that's a question of, well, if I don't actually know my real parameters, then it should be safe over a large parameter range. So you should make sure that the global sensitivity is okay, or that you found global optimal solutions. And you should be able to make sure that you can quantify your uncertainties and propagate uncertainties and optimize with respect to uncertainties. And so these are all different things that you need to do in a lot of realistic scenarios. And this is where compute gets really high, right? Because you can no longer say, like my parameters are good. You say my parameters are 1 of 500 million. And let's take everything that we've done in this course, take everything with our GPU parallelized ODE solvers, and now let's run that on multiple computers all simultaneously. Some of these examples in the end, we might not be able to actually run the code as part of our course because you need a lot of computers and a lot of compute power to do that. But you'll have all the tools and you'll have all the knowledge that you need to use that in your own problems. So the homeworks will come out as they're available. There will be the first homework coming out quite soon, by the end of the week. And so this is really what the homeworks are there to do, is they're just there to make sure that you're following along. If you understand the topic, The homework might take just one night or 2 nights. If you're learning the topic from the homework, it could take quite a while. So hopefully there really shouldn't be anything that's busy in there. You should be able to sit down, and if you know the thing, you can get it done. And so if it's not working out, really just stick your head in there and try to figure out what is going on with the way that you're understanding the problem. Because a lot of these, if you understand the problem correctly, the code should be really quick. And from the other times I've taught this course, there's this huge variance in how long it takes people to solve some of these problems, really just because it's, once you see the solution, it's a quick path to there. So it's kind of like the way that people finish their PhDs, right? A lot of people do the most of their PhD in the last year, just because it takes a while to do a lot of the learning, and once you know what you're doing, boom, it's done pretty quickly. So don't be scared by the homeworks. I know that some people were a bit scared before. Just ask a lot of questions, right? This is why we have these Slack channels set up. This is why we're going to have a lot of these office hours. Really what they're there to do is they're to get you on this path, so that way you will know how to do, you will know how to write GPU parallelized algorithms for training and control ordinary differential equation in a way that you're not actually even using a library, right? You could do the whole thing from scratch as part of what we'll be doing in this course. And then, of course, for your actual research, you can go pick up a library, but you'll know what every single detail is, and you'll know how you can open up the library at that point, and you can probably improve the library because you'll know how the internals work. So that's my big overview of what the course is going to be about. And our next video is going to be jumping into what is we're going to get everyone working, so that way you have an installation of Julia and you can start using the programming language. And we're going to jump into 2 topics, which is what is scientific machine learning and how do you start to parallelize serial code. So just to note, it's not going to be one lecture video for each lecture. Instead, we're going to cut it up, and we're going to really use this asynchronous format. So some of these videos will be 30 minutes, some of these videos will be an hour. If you don't have time to watch everything on the Tuesday and Thursday that it's assigned, or Monday, Wednesday that is assigned, that's okay. It's going to be totaling about the same hours as normal, but it's going to be chopped up in a way that makes more sense with the topics and the lectures that we'll be handling. So don't just be on the lookout for the 2 videos a week. It might be one video, might be one very long one, it might be 4 videos that are a bit shorter. You'll be getting emails as they start to come out, so don't worry about following it. It will all show up on this page down here. So it'll show up on this page with the lecture notes. In total, that will be the whole written out thing along with a video for you to follow along. If you feel more comfortable with videos, watch the videos. If you feel more comfortable just reading, all the same topics should be captured in the summaries and handouts that I'll be giving. So you can use either one or use both of them. I recommend using both of them, but some people just learn in different ways, and that's okay. So thank you for coming to this first lecture, and hopefully this is going to be a very nice course.